Okay, so good morning. My name is Gabor Bella. I come from Trento. I'm a researcher at the University of Trento, for those who don't know me yet. So let me start by saying a few words about our research group. So the group is called KnowDive, which means knowledge in diversity. And we are indeed quite a diverse and big group. We are over 40 people, actually. Under the direction of Professor Fausto Giunchiglia. And he was supposed to be here, as well as the postdoc Essence Fellow, Mladen Jovanovic, but unfortunately they couldn't come for various reasons, so I'm the only one here representing the University of Trento. And my talk will be about open data integration. So this is the title of my talk. It might seem a little bit cryptic at some places, but I will introduce the concepts one by one, and hopefully by the end of my talk you will have at least understood the title. Okay, so let's start with open data. So I think I don't need to introduce that. Everybody knows what open data is about. And probably a lot of you also know about this 5-star rating scheme for open data that Tim Berners-Lee has come up with. So where 1 star means that the data are just published online in whatever form. 2 stars means that the data are actually structured and readable by machines. 3 stars means that they are published in a non-proprietary format. 4 stars that they are actually identified by URIs. They are available on the web, of course. And 5 stars means that the data are linked, interlinked. So actually it's at this point that the story becomes interesting. So up to 4 stars, there is not much scientific difficulty really. And at 5 stars, everything changes. Now, why does it happen? Because linking so linking can mean a lot of things. Linking can be done in a very trivial way and can be done in very subtle and fine-grained ways. But first of all, why do we want to link data? Because data get interesting and more relevant when it's put in context. So when it's related to other types of data. It's not by accident that in the last 10 years, the killer apps, the most popular applications have been mashups of data coming from different sources. So this is why we try to link data. Now, what do we link? What can we link? So I took this example from the Trentino Open Data Catalog, on which we are actively working right now. So they're from the province of Trentino. And this one is about ski lifts. So as you can see, it's in a easy to understand tabular format. Let's start. So what can we link here? We can link the whole data set itself. So we can say that we can situate it in a domain, so that it belongs to a domain of transportation or recreation, and I can link the topic, the title of the data set to a concept that I might have in a knowledge base, to the concept of ski lift. I can link the schema, so I can identify previously known data schemas that are the same or that are similar to the one that I'm processing. I can link data records, so I can find objects that I've already described beforehand somewhere, or somebody else has described them, and I can discover that the data record is talking about the same object. I can link attribute names to, again, to concepts existing in a knowledge base. I can link data values to data value can be a key, for example, which will link to another data record or another object. And I can even go inside fields, data fields, which contain text, and I can analyze this text, do natural language processing, and extract and annotate concepts and named entities. So all this can be done to open data. Now the question is, of course, how we do this. So our approach in Trento is that we try to do data integration. And data integration means having a sort of a unified view over heterogeneous data, producing this unified view. Now, so what do? We have a lot of data sets published by a given institution, a given public body, a given department, and we first of all try to obtain this unified view for these data sets. So for example, in this case of the province of Trentino, so far they have published between 600 and 700 data sets. So we start by integrating these, and then we continue integrating other data sets coming from other institutions, from other provinces, etc. And we are aiming high, so we'd like to integrate data from coming from different regions, coming from different countries. But if we do this, of course, we need to be multilingual. So we need to be able to integrate data in different languages. And the way we try to do this is by doing it on a conceptual level. So we move from the linguistic level to a language-independent conceptual level. And for this, we need, of course, some kind of semantics. We need to have knowledge described in a language-independent manner. That's why I have a knowledge base here on my very simple schema. And we do it in an entity-centric way, which I will describe in a second. I will explain what it means, but first of all, let me just point out something. So this is the essence network. So of course, we understand that it is impossible to have an agreement on knowledge between very heterogeneous peers and that belong to different domains, that belong to different countries, different cultures. So we are not trying to integrate knowledge and facts into a single monolithic database. So this is a topic that has been researched in our group for years. I don't have time to get into the details about this right now, so I'm just mentioning the fact that the kind of architecture that we are planning to use is based on just a relatively small kernel of shared knowledge and shared facts, and then the actual peers can represent local knowledge, which don't need to mutually agree on everything. So this can be domain-specific knowledge, and there can be contradictions between local peers. So it's sort of a semi-distributed way of integrating knowledge and facts. Okay, so let's come back to this entity-centric bit. So what do I mean by entities? We use the word entity for objects that commonly appear, that we commonly refer to by names. So not every object is an entity. So if I take a chair, just any chair, it won't be. It's an object, but it won't be an entity. But if one of these chairs is somehow very special, and I want to talk about it, and I apply a name to it, then it can become an entity. So, so to describe entities formally, we need some kind of structure, and this structure we call entity types. Just to introduce a new notion here. And by entity-centric data integration, we mean a form of data integration where the unit of manipulation of data and the storage is the entity. So this represents a kind of a choice of granularity. Okay. So a little bit more specifically, more technically, how do we do this? So our group is quite practically oriented. So we are not interested in doing just theoretical research. We'd like to, at the same time, produce actual systems that work. So we have a kind of a pragmatic approach here. Because data integration in general is considered, so it's a very widely researched topic. It's been there for a long time, and it's considered to be impossible to solve at this time in a fully automated way. So we share this vision, and we are not trying to do it fully automatically. We are putting humans in the loop, so we are proposing a semi-automated approach where the system suggests solutions for data integration, and then the user verifies these and makes amendments. And this goes on as an iterative process. So we are developing a tool for this, data importing tool that is called Open Data Rise. And I'm simplifying here a little bit, but you can imagine it as a sort of a pipeline, an interactive or semi-interactive pipeline, which begins by so reading the open data from a given data set, doing schema matching, so where we are matching the schema of the open data set to our entity types in order to find to which entity type it corresponds the best. Then the schema matching is adapted by the user. Then we turn to the data. We do semantic enrichment, semantic annotation on the data, and we link named entities within data fields. And finally, we do entity matching. So that means finding to which entities the incoming data fields correspond among the entities that are already represented in our unified view, in our integrated entity base. So the challenge is to push this automation as far as possible, to require less human interaction. So in the rest of my talk, I will concentrate on just one box here, this box about schema matching, automated schema matching. So because the whole of it would be too complex, and then I would need to stay on a very broad level. So I prefer to go deeper here and give you some more theoretical insights into that. So let's take one simple example, where on the left-hand side you have again the schema of this open data set on ski lifts, but now it's in Italian. Now I didn't translate it to show you that we are actually trying to do multilingual schema matching. On the right-hand side, we have an imaginary entity type for facilities. And we are trying to find a match between these two. So find out which attributes on one side match which attributes on the other, and how. Now, this matching is of course not one-to-one. It's a one-to-many matching, because we have one incoming schema, but we have a lot of entity types on the other side. So if we take a brute force approach, we would need to do as many independent matches as there are entity types. Of course, there can be a lot of optimization on this level in practice. So what are the difficulties? The first problem is that matches will very rarely be perfect, of course. So we will need to quantify how much a given data set matches a given entity type. So give some quantified similarity measure in order to be able to compare them and say this entity type matches better than the other one. Another problem is multilingual schemas, not only between the two schemas, but even inside a single schema, open data schema, we can have multiple languages. And this is not an aberration. This is a very commonly appearing thing. So we encounter this phenomenon very often in the Italian data sets. So we can have half of the attributes in Italian, the other half in English, for example. Okay, and so for precisely because we are trying to do multilingual matching, we need to do it on the semantic level and not on the level of the strings, for example. So our group has researched semantic matching for years. I wasn't actually there because I only joined this group relatively recently, less than a year ago. But they started researching semantic matching around 10 years ago. And they actually created a tool for this, which is called S-Match. And it was developed initially for the matching of classifications, so web directories, for example, that classify resources, documents, etc. So I will, in the rest of my talk, I will show you how S-Match works and try to find out to what extent it is applicable to the problem of schema matching for open data. So I took a very even more simplified example here. On the one hand, I have again the ski lifts in Italian, and on the other hand, another schema, entity type schema for ski lifts. So this is a four-step process. The first step is about analyzing these labels in these trees. Yeah, this is something that I forgot to mention. So up to now, I've been talking about, I've been showing you schemas as trees. So this is not trivial. This is true for the vast majority of practical cases. So open data can come in various forms, in various data formats. So you can receive them as Excel sheets, you can receive them as XML files, etc. In most cases, they will be some kind of tree. The schema will be some kind of tree. In the case of a table, it will be a very shallow tree. In other cases, it can be a deeper tree. And of course, it's possible to have other structures. So if data comes in RDF, for example, then it will be a graph and not a tree. But that is very rare. So we are, for the moment, we are concentrating on trees. We are not trying to run before we can walk. So on the other side, we have our entity types, which are also trees. So I wanted to precise this to explain why I'm always showing you trees. Okay, so let's get back to SMatch and the first step of matching. So here, as I said, for every label that is expressed in natural language, we are trying to find the corresponding concepts. Of course, that means that we are using an external knowledge base. This is quite a complex process. I don't have time to get into the details, so it involves natural language processing, a lot of heuristics. And what we obtain for each label is one or more concepts. So these gray words in italics represent here concepts and not text, actually. So I can have single or multiple concepts, in which case we will construct a formula using these concepts, and the formula will depend on the structure of the text. So here I have a conjunction, for example. The second step is the computation of what we call concepts at nodes. The difference being that we take the formulas of the given node and take its conjunction with all the parents. So up to the root. So let's take the example of this end label. So the concept at label is end, and we take the conjunction of it with opening and our, its parent, and then the parent of opening ours, which is key-lift. So we obtain these formulas this way. So I don't know if you have noticed, but up to this point, we haven't yet done any matching at all. We've processed the two trees completely separately. So this means that, that this, up to here, this can be done offline in advance. There's no matching yet. The matching starts here in step 3, where we start to compare concepts appearing in both sides. And again, we are using an external knowledge resource which will tell us relations that hold between these concepts. So in my small contrived example, we might have an axiom coming from our knowledge base that states that name is a sub-concept of label. Maybe that's not true in real life. Maybe it doesn't make much sense, but let's suppose this for this example. So what we do is convert this description logic formula into propositional logic. And in step 4, we do the actual matching. So how is it done? We compare every node on the left-hand side with every node on the right-hand side. So we will need to do n times m comparisons. We fill in a matrix with our results. And the result will be 1 out of 4 semantic relations that might hold between these nodes, namely equivalence, subsumption, disjointness, or none of the above when we have no information, when we don't know. So what is how does it happen? For example, when we are comparing this node nome with this node label, we will test the subsumption relation in both senses. That will the both together will provide the test for the equivalence relation as well. And we will do a test for disjointness. And we do this by running a satisfiability solver on these formulas. So exactly what we are solving is whether our axioms imply this logical relation between the two formulas. So in the case of nome and label, if we are testing for a subsumption, then then our axiom, which is stated here, which I explain in step 3, should imply an implication relation between nome and label. So as you can see, the result of the matching, and so this is where the matching ends. The result of the matching is a set of semantic relations between the nodes. Now, this is not exactly what we are looking for open data integration, because we need something more. We would need some kind of similarity metric to be able to say that globally this schema matches well or doesn't match well. And we need to compare those matches. So this is something that's missing from this classical version of S-match. Another problem is that S-match was designed for matching classifications. This is inherent in the way which the formulas are computed, but open data schemas are not exactly classifications. So probably S-match would need to be modified to include these capabilities. Now there's another candidate, which is structure-preserving semantic matching, which was also invented at UniTN, among others by Fiona. And this is interesting to look at because structure-preserving semantic matching, which builds on the original S-match, actually provides a similarity measure based on a specific version of tree-added distance calculation. And it's called structure preserving because it preserves structure. What does that mean? So this SPSM was initially invented to compare services, like web services, which are formally described. And we want to match functions with functions and arguments with arguments. We don't want to match arguments with functions. So that means, in the case of trees, that means that we are comparing leaves to leaves and internal nodes to internal nodes. And we don't want to compare internal nodes to leaves. Now the problem is that in the case of open data, we don't always have this structure preserving condition. So in this particular case, for example, we can have orari, which is a leaf, and opening hours, which is not a leaf, and actually they should ideally be matched in this particular case, but SPSM doesn't do it because of the structure preserving condition. So this is to say that the S-match tool is an ideal candidate to start researching this topic, but it's not a final solution. So we are planning to work on this. And to finish my talk, I would like to broaden the horizon a little bit, because up to now I was only talking about schemas, but there are much more in open data than just schemas. So I couldn't resist including this famous detail from the famous fresco of Raffaello, where Plato and Aristotle are discussing schema matching. So Plato is saying you should look at the metadata, you should look at the schema, at the attributes, you should look at the intention. And Aristotle is saying, no, stay on the ground, look at the data. So Plato is, of course, an idealist, top-down, and Aristotle is bottom-up. And of course, probably the most clever thing to do is to try to combine both approaches and try to be as clever as Plato and Aristotle combined. So, which is of course a lot of people what a lot of people are trying to do, and we are trying to do this as well. So this is my last slide. And just to present you how we are trying to combine these two visions, the top-down approach and the bottom-up approach. So we can have our top-down metadata-based matching techniques on one hand, and we can have bottom-up data-driven techniques on the other hand that analyze the data and try to find out about the schemas from that. So a very simple example is data types. So we find out the data types. So if a data field resembles very much a date, then we can find out that the actual attribute is a date attribute, even without looking at the label. So combining these approaches probably gives us more robust results. So we do this combined approach first on the local level of individual attributes, and then we do it on the global structural level for the whole schemas, and then comes a human in the loop who will evaluate the results and make amendments and corrections. And this, the choices of the human are actually fed back in the loop, and that is why we have machine learning matchers, because they will improve as the user gives more and more feedback. And this is why a combined manual and automatic approach is particularly interesting. So thank you for the attention. Some reading material about this topic. Yes.
You haven't mentioned URIs at all, which sometimes, as identifiers, contain interesting structure.
Sorry, I didn't understand the beginning.
URIs are used often as identifiers for open data, right? In linked data.
Yeah.
So they contain semantic structure sometimes, because often they are essentially paths through a tree.
Yeah, right.
And
You're right.
I don't know if you come across the Silk workbench that Chris Beeser's group has developed in Berlin. They've done a lot of work on link matching, approximate matching down at the data values.
Yeah.
Using a combination of heuristics and rules and string matching.
Yeah.
And I was wondering whether you'd looked at that and thought you could integrate it into your approach.
No, we haven't looked at that. So at that particular work, but of course we know that this is not so. What I presented here, this combination of different top-down and bottom-up approaches, is not new, of course. So so there are actually lots of matchers existing, lots of very widely different techniques, and we are still at the beginning of our work. So we started this just a couple of months ago, and we are still in the phase of looking at various approaches. So we have a very first prototype demonstrator that works, but the bulk of the research is yet to be done. So we will have a look.
I was wondering what the notion is of and the relevance of context is. So, I mean, of course, I mean, one argument is not to try and map and match entire ontologies because that's not necessary and way too complicated. But on the other hand, it seems very extreme to try and match, like, you know, one very small schema in isolation from everything else, because everything else that is around it very often gives you constraints that further help you filter out lots of things that are not possible, and actually inform your matching. So I was wondering if there has been any work, or if you're interested in kind of exploring to what extent you either broaden or narrow down what you're trying to match to capture, I mean, to disambiguate, because I can see that sometimes it's not just a subtree, it's also the superstructure that helps you disambiguate, right?
Absolutely, I agree. Absolutely, and yes, we are trying to do that. So already, actually, these tree matching involves a lot of natural language processing, and in that we can in words and disambiguation, for example, we take context into account, and the context can be the already metadata of data sets, which provide descriptions on what the metadata, what the data set is about. And also, so words and disambiguation is we know that it's an extremely hard thing to do when we are doing it in general. And especially in these cases where we only have short labels and relatively little context. So we absolutely need to situate this disambiguation in domains. So in the case of having ski lifts, for example, it makes much more sense to do disambiguation in the domain of this particular data set and not try to do it in general. So that's the context.
I think also very often simply when you do the matcher will not work in isolation. It works as part of some application of something you're trying to achieve. And even just co-occurrence with other things gives you many, many filtering possibilities. But it would be interesting to see how you can take it into account algorithmically. I mean, not because, of course, you can build some component on top, which also uses something else. But the question is, can you also use it and change the heuristic or something? So.
Context in the form of concepts. So giving a set of concepts that relate to context, providing such a context for NLP and words and disambiguation is something that we already can do. So we actually do this, and we for words and disambiguation we use, for example, distances in the ontology in the ontology hierarchy. So distance concept distances can be used. And another thing that I'd very much like to do is the detection of the domain. So what domain are we situated in, and to ease the process.
Do semantic matching or ontology matching, but one of the things that we do at Clients is, okay, we have a document and we try to carry out semantic annotation of the document just to provide search functionality, right? So one of the problems that we have is that we have ambiguities. Okay? We are table, even in most of the cases we work with domain ontology just because it's better for the purpose of the application. And we try to apply general disambiguation, as Labor said, and the performance was quite low. You know that some approaches are trying to use Wikipedia to get the contextual evidences given an entity. And as I said, the performance was quite low. And what we tried was to use the semantic distance, okay? Trying to get how related entities within the domain ontology, which is focused on a particular domain, might disambiguate the annotation process. It was better, but one of the problems that we have is that you have to manually define what the domain is and how disambiguation is. So we would like to, for example, one of the things that we would like to do is something similar to what Gaber said, trying to distinguish between the different domains in some automatic way. So we don't need to define all the process, all the heuristics, for example.
Okay.
Yeah, I was wondering, so another group in Trento was using, well, about lexical semantics. They're using distributional semantics by the group of Baron Kelly. I mean, it's also about, well, how related are words, and maybe, so using contextual methods. Is it used in this kind of work as well?
I understand lexical semantics. I don't understand distributional semantics.
Well, that means that the meaning of a word is, well, basically the context in where it's used. How close? So the meaning of a word is how many times it's used together with in the context of another word.
Yeah. Yes. So this is something that we are not doing yet, but that I would very much like to do. So I would like to push research on word sense disambiguation as applied to short labels in this direction. And some other point that I wanted to make is that so all this needs, of course, very serious semantic resources, and lexical semantic resources, and language independent semantic resources. And we have been investing lots of man-years of efforts for developing these resources for specific languages. So we on the knowledge base level, we are distinguishing between lexical semantic concepts such as the synsets in WordNet, and we have also the difference of our approach is with respect to a lot of other people who are also using WordNet as a kind of an ontology, is that we think that WordNet is very much specific to English and can't be used as a general ontology. We need a language independent layer on top of it. So every language needs to have its lexical semantic resources, which are then interconnected inside with the independent layer. Thank you.